Hello everyone from Math 2000 Linear Algebra. It's Professor Wenson here again with a video on your ZyBooks Section 2.1 titled Matrix Addition and Scalar Multiplication. So this is an introduction to a new chapter on matrices. You may have seen a matrix before. It's just a rectangular array of numbers. Alright, well, you've definitely seen a matrix before, right? Augmented matrices in the previous chapter. But this chapter goes into more properties of matrices and operations we can perform with matrices. Alright, so here we have 2, 1, matrix addition and scalar multiplication. Alright, you can read this example. They go over here. You got the objectives. Alright, so remember how matrices can be represented. You have little brackets, and then if it's a capital A matrix, if the matrix is called capital A, very often they call each entry of the matrix a lowercase a, and then the subscripts tell you what row and column you're in. Alright. This is defining our matrix addition here. What does it mean to add and subtract two matrices? So two matrices A and B of the same size. That's key. They have to be the same size. So rows, same number of rows and columns, are added or subtracted by simply adding or subtracting the corresponding entries. And then it's denoted this way. Matrix A represented by this bracket with the Aij, plus matrix B represented with the brackets and Bij, equals, and then a bigger, a new matrix, so new set of brackets with Aij plus Bij, or if you're subtracting Aij minus Bij. All this is telling me is that, again, you're just adding or subtracting elements from these matrices that are in the same positions. And then huge one here, right? I said same size. They have to be of the same size in order to be able to be added and subtracted. Matrices with different sizes, right? Different sizes cannot be added, right? So they show you an example here. So like here's a 3 by 3 matrix plus a 2 by 2. See the different sizes? So this is undefined. There is no sum. There is no result here. You cannot add matrices with different sizes. Alright, so I'll show you an example on paper. This first participation activity, I have that written out. Okay, so here's the first participation activities example. I'm asked to see there are two matrices here. There's a 2 by 2 plus another 2 by 2. Right, so these matrices, they do have the same size, meaning they can be added. That's an A, sorry. They have the same size. That means they can be added. And when you add two matrices that are the same size, the result will also be that size. Okay, so a 2 by 2 plus a 2 by 2 will be another 2 by 2 matrix. All right, so there are 4 positions to fill. And it's very simple. You just simply add corresponding elements. So the first row, first column of the new matrix is the sum of the first row, first column entries of the other the matrices you're adding. So 3 plus negative 2 will be which is just 1. So 1 will be the first row, first column entry of the sum. The first row, second column is simply the sum of the first row, second column entries. Negative 4 plus 8. So that's positive 4. Second row, first column is the sum of the second row, first column entries of these matrices here. 1 plus negative 5, which is negative 4. And finally, the second row, second column is the sum of the second row, second column entries in these matrices, 0 plus -3, which is -3. And here would be the final result, the sum of those two matrices. Very easy, very simple, I believe. I hope, hopefully you can get the hang of this real quick. The same thing would go for subtraction. All right, the only difference is I'd subtract all these values instead of add them. But adding and subtracting, same thing, right? So they go through that example there, right? Get the matrix that I just showed you. You can play the animation, right? Complete the activity. Cool. All right, so you can read through these examples. Like I said, with subtraction, I would just do 2 minus 5, 4 minus -8, or 4 plus 8. -2 minus 4, 1 minus 6, 5 minus 7, 9 minus -5, or 9 plus 5, and get a resulting 3 by 2 matrix, right? This is a 3 by 2 minus a 3 by 2. The result would be a 3 by 2. Okay. And you can also do this in your calculator. All right, I'm not gonna. Well, I'll do some later. But you can enter this matrix in your calculator, and this separate matrix as another matrix in your calculator, and then do operations on your main screen just like you would with numbers. Just add or subtract your matrices. And I'll show you that later. Example B here. See, this is a 4 row, 2 column matrix, 4 by 2, plus a 3 by 2. These don't have the same size, so you cannot add these. This addition is undefined for part B. You can do these, and then you can do more than 2 if you want, but see how all these have the same size in part D, 2 by 2 plus a 2 by 2 minus a 2 by 2. Just, you can make a new 2 by 2 and then take, 8 plus 3 minus -2, 6 plus 0 minus 0, -7 plus -9 minus 0, and then 5 plus 1 minus 1. It's very simple. And again, they go through the problems here. All right, then some true falses. I'll just do the first couple here. The sum of two matrices with the same size is going to be another matrix, not just a single number. All right, so this is a 2 by 3 plus a 2 by 3. It would be another 2 by 3 matrix, not just a number -1. So this is false. All right, let me go through and show you what it would be. Right. Here's a couple 2 by 2s. Again, I showed you an example, real simple. They're the same size. The result, the sum would be the same size. All right, and you got -2 plus 2 is 0. 1 plus -3 is -2. 4 plus 0 is 4. 0 plus -8 is -8. This is true. That would be the resulting sum, and hopefully, again, these are easy. You can go through those on your own. All right, then the other operation brought up in this section is, scalar multiplication. So a scalar, you're going to hear the word scalar a lot in the rest of the course. A scalar simply refers to a real number, such as 3 or -5.1 or pi or the square root of 2 or 7 or whatever, right? Just a number. Scalar usually also refers to, it's a scaling thing. It makes things larger, makes things smaller, especially when you're looking at pictures, right? Scales them up, scales them down. But when they say scalar, they're referring to it just a number. Okay. A scalar multiple of a matrix is a matrix in which each entry, right? Each entry is multiplied by a scalar, just a number, and they denote it here. If R is a scalar, right, R belongs to the reals, and A is some matrix with the entries Aij, then R times A, the scalar times the matrix, R times A is, R times the brackets with Aij, and that's the matrix, a new matrix, where every single entry, every single Aij is multiplied by the scalar R. So again, I'll write out the examples from this first participation activity and show you some again, it's pretty simple, I believe. All right, so these are the same examples in the first participation activity there. So when you multiply a matrix by a scalar, right? So again, this number out here, right? A scalar is just a real number. Right? So just a single number. Scalar. So this is a scalar of 2 multiplied by, a 2 by 2 matrix. Now, when you multiply a matrix by a scalar, the size does not change. All right, so this will be equivalent to another 2 by 2 matrix. All right, the size doesn't change. I'll just put 2 by 2 over here. Okay. And it's very simple. All right, you just multiply every entry in that matrix by the scalar. So the resulting matrix, the resulting scalar multiple, the first row, first column is going to be 2 times 1. The first row, second column of the scalar multiple is 2 times 0. Right? Then the second row, first column is going to be 2 times 3. And then the second row, second column is going to be 2 times -2. So the final result is 2, 0 for the first row, and then 6, -4 for the second row. Right? So this would be the final resulting matrix, the scalar multiple of that matrix, 2 times that matrix. Very, very easy. Same thing down here. This is another 2 by 2. Again, whatever size it is, whatever size the matrix is, multiplying by a scalar, you keep that size. So it's going to the result, the scalar multiple here is going to be another 2 by 2. And I'll just do it, out loud. -3 times 0, 0. -3 times 2, -6. -3 times 1, -3. And -3 times -1, +3. And there we go. And this is the scalar multiple. All right, you have the scalar -3 times this matrix here. Right. Very, very easy. You can play through the animations yourself. All right, so again, very simple examples. This is just telling me multiply every entry from matrix A times the scalar 3. This one here, you have a 2 by 4 matrix. So when you multiply by every entry by -2, it's still going to be a 2 by 4 matrix, and you see the result down here. Again, you can read that on your own. All right, now scalar multiplication, matrix addition, and matrix subtraction may be part of the same expression. So we can do them all at the same time, multiple operations in the same expression. The process for finding the result is similar to using the order of operations. Remember, order of operations, you do multiplication first, then addition. All right. So if you see something like this, -3b plus 2c, you do the scalar multiplications first, multiply by -3, multiply c by 2, and then add them together. All right. So let's so let me do that, this by hand. All right, I'll do it on a piece of paper, and then this is where I'll show you the calculator work. Okay. All right. So I'm doing this. That was matrix B from the example. Matrix C. They're both 2 by 2 matrices. And then what I'm doing here is the first example in that page that you saw there. -3 times matrix B plus the scalar 2 times matrix C. So again, writing this out fully, this would be -3 times the 2 by 2 matrix with the 0, 3, 0, -1. Right, that was matrix B. Plus, and then 2 times matrix C with the 2, 4, 0, 1. And as I said earlier, right, it's just like order of operations in basic arithmetic. Perform your scalar multiplication first. So I'm going to do this multiple and then this multiple. I'm going to do the scalar multiplication first. So we have here 0, -3 times 3 is -9. 0, and then -3 times -1 is +3, plus, and then this scalar multiple is another, again, a 2 by 2. 2 times 2 is 4, 2 times 4 is 8. 2 times 0 is 0. 2 times 1 is 2. And now I can add these again because they have the same size. 2 by 2 plus a 2 by 2 will be another 2 by 2, but this time it's just simply addition. 0 plus 4 is 4. Negative 9 plus 8, negative 1. 0 plus 0 is 0. 3 plus 2 is 5. And there we go. We're down to a single matrix. Here is our final result. Right, what that expression that is equivalent to. The matrix, this 2 by 2 matrix. Okay, now again, I'm going to show you this on the calculator. All right. So I'm going to pull up my calculator. And remember how to enter matrices. This is from a previous video. So I go second, right, matrix, over to edit. And because these are called B and C here, I'll just scroll down and we'll make matrix B the matrix that I have called B here. It's a 2 by 2. You enter the size, 2 rows, 2 columns. Put the entries in. Now the 0 is already there, so I'm just going to enter twice, and then you got 3, enter, and then 0 again, so just enter twice, and then negative 1. Alright, so there's matrix B. So I'm going to go back to the matrix menu. See, now there's this 2 by 2 matrix showing up by B. Go over to edit, and this one was called C, so I'm just going to call it, I'm just going to go down to matrix C here. Why not, right? And you could call it matrix A if you want. You can put it in whatever letter you wish. So again, we have a 2 by 2, and put these entries in: 2, 4, 0, and 1. Alright, and then now I'm going to quit this, go back to the main calculation screen, and now that I have the matrices I want entered, I can perform all sorts of operations with them. So I want to enter, say, negative 3 times matrix B plus 2 times matrix C like I have here. So I go negative, the negative sign, negative 3, and then times, and then I go to the matrix menu, and then under names, I use the matrices I want in my calculations, right? I want matrix B. So there's negative 3 times matrix B plus 2 times matrix C. Right, so back to the matrix menu, and then you could hit the number 3 or just go down to C there. And there we go, and then put enter, and you see that this 4, negative 1 first row, 0, 5 second row, exactly the same thing coming up in the calculator. All right. So again, please, don't rely on the calculator super heavily for this. I mean, this is just addition and multiplication here. This is some simple arithmetic. But you can use it to check that you're doing the right thing by hand. All right. Okay, so back to the page. So yeah, that was negative 3b plus 2c. Now how about a minus 5b? Now look at these. You're doing subtraction. Look at the sizes. A is a 3 by 2. B is a 2 by 2. They are different sizes, so part B could not be done. And you would see that in your calculator, right? If you entered these matrices in your calculator and then tried to do A minus 5B, it would come back at you with an error, a dimension error. The sizes are called the dimensions sometimes. So yeah, A minus 5B can't be done, undefined. A minus 4D could, right? Because A and D are both 3 by 2 matrices. So A minus 4D could, and I would leave that to you, or you could just read this here. Alright, then you're doing this, I'll leave this to you. Now, it's just like order operations, people. Alright, see this here? Where it's 2 times the quantity C plus A. That means do C plus A first, right, and then multiply by the scalar. And we'll also see in a second that you could also distribute the scalar, do 2 times C plus 2 times A, and get the same result. And again, I leave that to you to play around with these. Right, and that's what I was talking about here, properties of matrix addition and scalar multiplication. Right, some things that are always true as long as things are defined, right? As long as matrices have the same size here. So I'll just read these off. I'm not going to go over the proofs, okay? But let A, B, and C be matrices with the same size, right? And little r and little s be scalars, right? Just real numbers. So you have the commutative property, which simply is, it doesn't matter what order you add two matrices in, you'll get the same result. The associative property of addition, if you add three matrices, it doesn't matter what two you add first. You can add A and B first and then C, or B and C first then A, and you'll get the same result. You have the associative property of scalar multiplication, or just multiplication here. But see R times S times A, where you do S times A first, then times R, gives you the same result as if you just multiply the scalars first and then times the matrix. I mentioned this one a second ago, right? You can distribute a scalar over matrix addition. Right? If you have a scalar times the sum of two matrices, you can add the matrices first and then multiply by the scalar, or you can distribute the scalar and get R times A plus R times B. You can also distribute a matrix over the sum of two scalars. So if I'm adding two scalars, you can add the two scalars first and then multiply by the matrix, or distribute the matrix and multiply the matrix by scalar first and then add the results, and you'd get the same thing either way. And then this last one is hopefully, remember this bold zero? Remember when you see a bold zero, that just means the zero matrix. It's a matrix with all zeros for entries. If you add a matrix to a zero matrix, you're just going to get that first matrix back. Right? The zero matrix is called, the additive identity. All right, so hopefully some pretty straightforward things you can go through. Now they go through a proof. They go through a proof. And again, I leave this one to you if you read through that. If you read through the proof in their box up here, you should be able to probably work your way through what are the reasons for each of these steps in this proof here. All right, and then they go through some examples. Again, I'm not gonna. It's just addition and scalar multiplication. Very, very simple stuff. Some more true/false statements, so you have to figure this out. And then you have a matrix operations challenge activity. So I'll just do this first one again. They'll get more complicated. There are 5 of these. The first one is just simply add these two matrices. And I know on some of them it might say if it's undefined, it'll have you click a box or type undefined. But these are both 2 by 2s. So that would be -8 plus 0, or just -8, and then -4 plus 6 is 2, and then -1 plus 5 is 4, and then -2 plus -7 is -9. I enter all the entries in the resulting matrix. Cool, it takes me through what happened. I hit next, and then it takes me to the next one. Right. And here, this is subtraction, right? And again, they're going to get a little more complicated throughout them, but no, not so bad. All right. And I guess the only thing I have to say about this is remember that when we're talking about matrix addition and scalar multiplication in economics, profit, right? Profit is the amount of money, it's the net amount of money earned by your company. The profit a company makes is the amount of revenue, right? Revenue is money brought in minus expenses, right? How much money you're spending, how much money you're throwing out. So it's the money taken in, the revenue, minus all the money you spend, all the costs. Right? So it's revenue minus costs gives you profit. If you remember that, it should make this part a little easier. So they give you an example here, and I'll just go through the participation activity with you. So here's some matrices. A small bookstore has 3 departments: new books, used books, and a coffee shop. The quarterly revenue, right? Again, revenue is money brought in, the money they made off sales or whatever. inventory costs, so that's money they're spending, that's money going out, and payroll costs, right? So that's another cost, that's another amount of money going out, are shown in the spreadsheet below. Find the quarterly profit from each department. So see this revenue matrix, it's a 3x4 matrix here. You got the new books department brought this much money in each of these quarters. Pardon me. The used books department brought this much money in each of these quarters, and the coffee shop department brought this much money in each of these quarters. Then you have another 3x4 matrix representing inventory costs, right? This is money spent on inventory by the departments in each quarter. And then payroll costs is also money spent, right? How much they're spending on their payroll, paying their employees each quarter. All right, so you got these 3x4 matrices here. Now the data represent, all right, so the data can be expressed as matrices, and like I said, each of these can be a 3x4 matrix, and let's just make sure the numbers match up. So you see R here for the revenue. This was the money brought in by each of the department, where each row is for, the first row is for new books, the second row is for used books, the third row is for the coffee shop, and then each column is for the quarters, right? The first column is for the first quarter, then second quarter, third quarter, fourth quarter. And it looks to me like the numbers are matching up for the revenue. That's the top matrix here. Looks like the numbers match up for I. I is for, inventory costs, this matrix I here. And it looks to me like those numbers also match. And then C for just payroll costs, C for costs. I don't know why they didn't use P, but whatever. It looks like the numbers match there as well in all the rows. So yeah, I could express all those as those three matrices. The profits for the bookstore are calculated as, P. Okay, I see why they didn't use P earlier. They're using P here for the matrix for profits. The profits matrix would be revenue plus inventory costs plus payroll costs? No. Remember I said earlier, and again, if you read the example from earlier, they talk about revenue minus, you subtract costs. You take the amount of money you made minus the amount of monies you spent for profit. So here, this is not going to be a good matrix for the profits, right? You don't take your revenue and then add how much you spent. You take how much money you made, the revenue, and then subtract how much money you spent to get profit. So this would be false. Right? And they show here it should be revenue minus inventory costs minus payroll costs, right? You subtract the cost. And then the coffee shop had the highest profits for the three of the four quarters. All right, so in this one you would actually have to do R minus I minus C and see which one has. Now let's see, if I take the new books department, the first row, and subtract, you get R minus I minus C. That would be negative 1,000. It lost $1,000 in the first quarter. And you would subtract, basically you would subtract these matrices, R minus I minus C, and then see if this statement is true or not. Does the coffee shop have the highest value in profits in the three of the four quarters? All right. So what I'm actually going to do is I will put this in my calculator and bring it back to you. Okay, so what I did was I put these matrices in my calculator, but I just put in 17, 15. I just put in by the thousands, and then did A minus B minus C. I call these matrices A, B, and C in my calculator. And you could do this by hand as well. It's just a bunch of subtraction. And let's see. If I look at these columns here, the highest profit in the first quarter was from the used books department, the second row. The highest profit in the second quarter was from used books. The highest profit in the third quarter was from used books. And the highest profit in the fourth quarter was the coffee shop. So the coffee shop only had the highest profit in one of the 4 quarters, not 3 of them. All right, so this is a false statement. And again, they do the subtraction and all that. Yeah. See, the coffee shop had the highest profits only in that 4th quarter. Right? Not the first 3 quarters were all dominated by the used books part, the used books department. Yeah, and that's it. All right. Then you have your additional exercises, which again you can view the solutions to if you wish. Some of these are part of your 3rd assignment that I'm gonna that I want you to write out and upload to me. And there's other ones in here that I didn't assign, but I still recommend you do everything. Right? Try to do every problem just to get more practice. That's the only way to get good at these things. And I try to say this every video. Please try to work these out before you look at the solutions. Just to check yourself, see that you know what's going on. Because if you just copy down solutions and that's it, you're not going to learn anything. You need to practice and do this stuff on your own. And the same thing goes for the activities. Don't just guess on them. Right? Don't just guess. Actually try to figure things out on your own and then put in an answer and see if you're correct. Because you're not gonna learn anything if you're just copying down a bunch of solutions. All right. So that's it for section 2.1. This introduction to matrices, matrix addition, and scalar multiplication of matrices. You'll see here the next section is matrix multiplication. So this isn't scalar multiplication. This is multiplying one matrix by another matrix. And it's a little trickier than it sounds, right? It's not as straightforward as matrix addition is, right? Or as scalar multiplication is. It's a little trickier, and you'll see that in the next video. All right, so thanks for watching. Hopefully you get through section 2.1 pretty easily, and take care.